Cornell. She'll be finishing her PhD next year. And at Cornell, she's been working with Professor Dong Lei on tides in eccentric two-body systems. On Monday, she actually gave a talk about gas giants. Today, she'll instead be telling us about white dwarfs very close to big black holes. She'll be visiting to the end of the day if you're interested in meeting with her afterwards. And so Michelle, take it away. She'll be telling us about eccentric paths to tidal disruption.
Thank you very much. So I'll be talking about tidal dissipation in white dwarfs around massive black holes. This is a project that I've been working on with Dong Lei, and some of, I think all of this work really is in a few papers that are published in monthly notices that I've put down here. So this is, next few slides are preaching to the choir a bit, but just to give the background. So tidal disruption event occurs when a star passes too close to the black hole and is torn apart by tidal forces. The debris from the star falls back onto an accretion disk around the black hole and creates a light curve that decays with a distinctive power law, the T to the minus 5/3. It's predicted in a few kind of more classical papers now, I guess. And this is, these events are interesting to study, especially now because there are many active and upcoming transient surveys that are poised to detect a lot of these events. A few kind of are displayed here. And now I'll get into specifically why tidal disruption of a white dwarf is an interesting thing to study. So for one, tidal disruption of a white dwarf should be very bright, visible from cosmological distances. But it's also only visible if the black hole is intermediate mass to moderate mass, so maybe under about 10 to the 5 solar masses. If the black hole is more massive than that, then the disruption would occur within the Schwarzschild radius, so we wouldn't actually see anything. And this system is also interesting because some types of these systems might produce a gravitational wave signal that could be detectable with a space-based interferometer like ELISA. So this is a candidate for kind of a dual detection of the gravitational wave signal and an electromagnetic counterpart. And there are a few kind of candidate white dwarf tidal disruption event observations. These are mostly sort of puzzling transients where it's been proposed that maybe what we're seeing is the tidal disruption of a white dwarf. So there's kind of one more recently, just this last year, and there's also been a few suggestions that ultra-long gamma ray bursts, these bursts of duration about 10 to the 4 seconds, might be signatures of white dwarf tidal disruption. And now to move on a bit to some theory. So typically the way that you would think of a tidal disruption event is that within kind of a single passage, a single close encounter, the star is torn to shreds by the tidal forces from the black hole. But what if this separation is actually a little bit larger? It's large enough that the white dwarf, in this case, can survive an encounter, but still small enough that you have a really strong interaction between the white dwarf and the black hole close to pericenter. So you still see some very interesting tidal effects that can change the structure of the white dwarf, or maybe even the orbit, more likely the structure. But the white dwarf is able to survive kind of multiple orbits. And this is the case where when you're completing multiple orbits, this is the kind of system that you might actually expect to see a gravitational wave signal from. So this is the general setup for the problem that I'm studying, is that at pericenter, the tidal force from the black hole will excite oscillatory modes in the star. So I refer to these oscillatory modes as dynamical tides. That's what I mean when I say dynamical tides throughout the talk. And when this happens, you transfer some energy and angular momentum between the orbit and the star. And the amount of energy change will depend on kind of this separation. The smaller the separation, the stronger the interaction, the more energy transfer. And I want to understand how these dynamical tides affect the structure of the white dwarf over multiple orbits. So when you're transferring some energy, the energy has to dissipate somehow. You have some tidal heating. So the question is how this tidal heating affects the white dwarf. And you can imagine that there might be things like maybe that you can even kind of ignite some fusion in the outer envelopes of the white dwarf. There might be some, like, a bit of inflation and mass stripping. There's a lot of interesting things that could happen. But before you can answer that question, you need a good prescription for how the white dwarf is dissipating energy. And that's what most of my work has been about. So we'll start with kind of the simplest treatment. So just examining these oscillations that are excited in the white dwarf in a linear way is a good starting point. So in this picture, you can describe the oscillating modes with the mode amplitude. And this mode amplitude has a magnitude and it has a phase. And the phase is actually quite important over multiple pericenter passages. The phase of the mode at pericenter will affect kind of whether this energy transfer is additive or even whether you're kind of giving some energy back to the orbit. So in some cases, there can be a back and forth. And you can characterize the mode by a few properties. The frequency is, of course, important. So for this problem, we're looking mainly at the fundamental mode of the white dwarf, but also gravity modes. So these are lower frequency oscillations where buoyancy is the restoring force. So you can also describe the mode with a damping rate. So this would be kind of radiative damping is relevant here. And with a tidal overlap integral. So this quantity just tells you how strongly the mode is responding to the potential of the black hole. And this is the largest value for the F mode and kind of drops off pretty steeply as you go to higher order gravity modes. In order to evolve this system with the linear treatment, you need a few things. You need an equation for the time evolution of each mode, and you need an equation for the orbital evolution that will depend on what's happening with all of the modes. So this kind of coupled system is, you can write out an equation, you can integrate it, but it's a little bit tricky to integrate just because the most interesting timescale is the pericenter timescale, but really you're evolving over the whole orbital period, which for an eccentric system is much longer than the pericenter timescale. But fortunately, there's a tool that you can use to kind of help you do this more efficiently. So for a highly eccentric orbit, where you have the strongest interaction just at pericenter, you can kind of reduce the situation to an iterative map, which is basically where if you know kind of what the oscillations, if you know what the system is doing just before one pericenter passage, you can calculate what it will be doing just before the next pericenter passage, using this kind of impulse approximation where interaction is occurring just at pericenter. Here's just a quick repeat for people who saw the talk on Monday, just a few slides in common to go over what's important for this iterative map, so bear with me here, I apologize. But the key parameters for this kind of mapping or for the system are going to be the initial orbital period, and of the damping rate of the mode, but most importantly, how much energy is transferred in the first pericenter passage. And this is a measure of how strong the interaction is between the black hole and the white dwarf. So this is like if you start out just before pericenter here, and now you've moved through and excited some oscillations, there's now some energy in those oscillations. And you can think of this in terms of a phase shift. Any fractional change in the energy of the orbit is going to correspond to a fractional change in period, just from Kepler's law. And if you multiply that by the mode frequency, it gives you a phase shift. And this quantity is really important. Kind of how much this energy transfer affects the phase will tell you what the behavior of the system is on long time scales. So now we ask what the mode energy is doing over many orbits, just taking a case where there's no dissipation just for simplicity. So the first kind of behavior that you see is you have this sort of gentle back and forth. So this is the mode energy, units of orbital energy, and here's the number of orbits. So this occurs if you have this small phase shift or not a lot of energy transfer at pericenter. In this case, it's just kind of oscillating mode energy. Nothing too interesting is happening yet. In the case where the mode frequency happens to be some integer multiple of the orbital frequency, you see something a little more interesting. Then you can see a kind of resonant interaction. So you reach higher energy amplitudes in the modes, but it's still this back and forth. But the most interesting behavior comes when the phase shift from energy transfer at pericenter is large. So when there's very strong interactions between the black hole and the white dwarf, then this energy can climb very quickly within a few orbits. So far we've been using a linear treatment of this problem, but it's fair to ask if you can have behavior like this, which you can for kind of smaller pericenter distances, but still outside of the tidal disruption radius. In that case, then maybe you need a way to handle kind of non-linear behaviors for these oscillations. That's the next part of the talk is kind of introducing a way to calculate a tidal heating rate when you have non-linear behavior. So a way to start with this is to look at the propagation diagram for the white dwarf. So here this is just kind of moving from the center of the white dwarf to the outer radius. There's shown on this plot the density and also a few frequencies, but the most important one is here is the Brunt-Väisälä frequency. So this is the frequency where if you are in a radiative region and you displace some parcel of mass by a little bit, it will kind of bounce around back and forth at this frequency here. And it's an important frequency because beneath modes can propagate kind of underneath this frequency cutoff. So sort of within this range, that's where G modes can propagate in the white dwarf. So these are the modes that you're exciting in these pericenter passages and that determine how much energy is transferred and what happens with tidal heating. So when you have kind of two reflective boundaries here, then you have the conditions for kind of just a standard like normal mode. So you have discrete normal modes, kind of like if you have, I guess, sound propagating in a tube, kind of similar idea. However, if you don't have, or you'll notice that the oscillations can grow in amplitude toward the surface of the white dwarf because as the density falls off, the amplitude, this is the Lagrangian displacement, or you can think of it as the amplitude of the oscillations, is going to increase really steeply. In that case, maybe you don't have this outer reflective boundary. Maybe a better way to think about this is as kind of exciting an outgoing gravity wave. So now rather than discrete modes, you're looking at some compositional boundary here, maybe from this transition to helium or from helium to hydrogen. You're exciting some outgoing gravity wave, and that will carry away some angular momentum flux and some energy flux. So to get the tidal heating from this, kind of have this formalism where you have this outgoing gravity wave. So this is actually from a calculation using the white dwarf model on the previous slide. And you assume that at some point this amplitude becomes too large and any angular momentum, any energy that was kind of moving outward in this wave is now deposited somewhere here at some depth close to the surface. So we've chosen an envelope depth about 10 to the minus 4 masses, but that's kind of parameterized. More work could go into figuring out exactly where you'd be depositing this heat. But this gives you a way to calculate a heating rate and a luminosity change due to tidal heating. Well, a good starting point for this is to look at kind of the circular problems. This has been done before in the context of a white dwarf binaries for solving for kind of what tidal dissipation you see in that case. So here you have just the quadrupole potential written here. So this is the potential that's exciting the gravity waves. And you can, when you solve this for the angular momentum flux that's being carried by the waves, you get this expression here. But it depends on the forcing frequency of the potential. And it also depends on kind of the mode amplitude. This is determined by the strength of the interaction between the black hole and white dwarf in this case. So it'll be something like kind of this m over a cubed quantity squared. And you can evaluate how much angular momentum, what the value is of this angular momentum flux near the surface, and get a dimensionless tidal torque. And then you can write angular momentum transfer and energy transfer in terms of this dimensionless quantity, which you can calculate for a white dwarf model. So you can calculate how the model responds to this frequency and then just kind of scale it with the appropriate physical units to get a value. So here this big omega is the orbital frequency. The forcing frequency for the circular case, just twice the orbital frequency. And just to kind of drive this point home again, so this is what's happening to the wave that you've excited. And here's just a very simplified version of the complicated Brunt-Väisälä frequency that you saw before, just as a kind of a toy model to see what happens. So you have, what's causing this behavior is you have kind of a jump in the Brunt-Väisälä frequency. So then you excite this wave that grows in amplitude toward the surface. And if you look at the energy flux, or a similar picture for the angular momentum flux, it jumps to some constant value where that wave is excited. So then you pluck this value right here, and that tells you what the response is. So then you can kind of look, you have this very simple, or not really, response of how the white dwarf is responding to different frequencies. So you can kind of map that out. For an eccentric orbit, you basically do a similar thing, but now instead of thinking of the potential as forcing the white dwarf at a single frequency, you write it as a sum of multiple frequencies. And this sum is just weighted by Hansen coefficients. This is kind of a standard way of looking at an eccentric orbit. And now these expressions look complicated, but really all we've done is you take this response to a forcing frequency and weight it by this Hansen coefficient and just add that up for all of the relevant forcing frequencies in the eccentric orbit. And the more eccentric the orbit is, the more terms you need to include in the sum to have an accurate result. So you can calculate the angular momentum transfer rate. This will tell you something about how quickly you're spinning up the white dwarf. It turns out to not be too important here. You can calculate energy transfer in the inertial frame. That tells you something about kind of the feedback on the orbit from this process. But most importantly, you can calculate how much energy transfer is happening in the rotating frame of the white dwarf. And that tells you something about tidal heating, which is the main point of this. So now when you calculate these energy transfer rates, you can kind of compute the sums from the previous slide, and you get something like this. So this is just, the dimensionless form, so we've divided off kind of this prefactor here. That's all we've done. And you can see that as this parameter is kind of a substitute for the pericenter separation increases, as you would expect, the energy transfer falls off. So this one is most important. This is tidal heating here. And you can look at this for a few eccentricities, for a few kind of values of white dwarf spin. But the main story is that, kind of surprisingly, I had no reason to expect this, but the way that this changes with the pericenter separation is just kind of simple exponential decay, which is nice because now you have kind of some equation that you can just put in for how is tidal heating changing as the orbit decays, which it will be doing from gravitational radiation, which is kind of the next slide is the main point. So these are the implications for tidal heating of the white dwarf in the system. So you might ask, what happens when you couple this kind of tidal heating with the orbital decay from gravitational radiation? So we've done this using just a MESA-generated carbon oxide white dwarf. And these plots here, this is eccentricity, pericenter distance, and units of tidal radius, and the orbital period. This is just following the pathway from gravitational radiation. So shown, the three different lines are three different initial separations. And the tidal disruption would be when this parameter is about a few. So these are all kind of well outside of danger of tidal disruption. And when you add in the heating term on the white dwarf, you can look what happens to the effective temperature for these three cases, starting out at three different separations. And you see that the effective temperature increases pretty steeply. And these different lines here are showing kind of different assumed envelope depths for where you put the heating, just to show what happens if you wiggle that parameter around a little bit. But you'll notice that in all of these, I've kind of cut off the calculation here. And what happens there is you've actually started some runaway fusion in the outer hydrogen envelope. So if you look at kind of how much power is happening in hydrogen burning in the envelope, you can see that kind of spikes at this point. And the time step that you need to evolve the structure of the star shrinks down to a very small value. So we say at this point, you've ignited fusion in the hydrogen envelope. And this happens well outside of the tidal disruption radius. So this might be kind of like a mini nova. It turns out that it's not very bright because the temperature is increasing. It's a factor of a few. So The brightest you might expect is maybe kind of some fraction of a solar luminosity, but the implication is that kind of a white dwarf that takes this pathway should have lost its hydrogen envelope well before it is tidally disrupted. And just to kind of put up a summary of the talk. So the main points would be that a star in an eccentric orbit around a black hole can exhibit a variety of dynamical behaviors depending on the pericenter distance. So a lot of kind of interesting things can happen and the strength of tidal heating. And we have a technique where given a white dwarf model, this could also be applied to other types of stars, but given a white dwarf model, you can calculate a tidal heating rate for a given orbital parameters. And in particular, you have a very kind of simple way to do that, if I move back here, sorry, where you can actually kind of write just a simple exponential decay equation for that and easily plug that into kind of some orbital evolution to figure out what's happening to the star. So it's numerically a very easy way to do that, which is nice. And back to conclusions. And the last point is that for the specific case of tidal interaction between a black hole and a white dwarf in an eccentric orbit, you would expect the structure of the white dwarf to be significantly altered. There's significant tidal heating even when the white dwarf is pretty far from kind of the tidal disruption radius. So you would expect the white dwarf to lose its outer hydrogen layer if it has an outer hydrogen layer well before disruption. Thank you for your attention.
Questions for Michelle?
As we observe a tidal disruption, how do we know that it's a white dwarf and not a normal star?
Yes, so there's a few signs. So one is just kind of the brightness of the event, but also I think for a lot of these, for an event that could be tidal disruption to a white dwarf, you would expect to launch a relativistic jet, so that might be one signal is that you could observe the higher energy radiation as well as kind of seeing
A relativistic jet that we could see with the telescope?
Yeah, a telescope on the right wavelength, I guess. So we'd see like more high energy, like gamma ray, X-ray.
Maybe I missed this, but what is the range of orbital periods that we are using in the calculation?
Oh, the range of orbital period, great. So, yes, so going back to this figure. So I have to do like the translation. So the pericenter frequency is going to be kind of more in the realm of I think like thousands. I think the answer to orbital periods is like kind of in the realm of hours. Yeah, so
very
this is the short.
ultra-compact binaries.
Yeah, here's the log period in seconds.
But then you talk about the circularization of these orbits, like in this scenario.
Right.
Do you talk about the circularization, or they never circularize?
Oh no, so they do circularize somewhat. As you can see, this would be kind of what's happening to the eccentricity from gravitational radiation. So the figures I showed before with the heating rates were for higher eccentricities, but we've done that for like a range of eccentricities, so you could track that as the eccentricity evolves.
Anyone else? Okay, let's thank Michelle again. So our next speaker is Francesca Civano. She's an astrophysicist here working at the Chandra X-ray Center in the Data Systems Operations. She does a lot of work on the Chandra source catalog, and she's really interested in multi-wavelength surveys, studying the connection between galaxies and supermassive black holes. She's a big fan of very large surveys, especially the VLA-COSMOS survey, which when I started working with her as a postdoc a couple of years ago, she told me is the greatest survey ever, and as I've come to learn over the past couple of years, she's always right. Francesca got her Francesca
behind.
It's recorded.
That's it.
Francesca got her PhD at the University of Bologna.
It's okay.
That's it. That's all she needed from me. She was then a postdoc at Bologna, and then she came here to CFA. She was then a research associate at Dartmouth and Yale before returning here again. Today she's going to be telling us about searching for intermediate mass black holes.
Thank you, Francesca. So I'm going to tell you about this work that I've been doing together with Mar Metzqua and some the other people listed here to search for intermediate mass black holes in dwarf galaxies with both X-ray and radio data. I will have a little bit of introduction and then show you the results of a series of papers, last of which was just submitted last week, so very new. So we all agree that black holes are ubiquitous in local galaxies, and now we have also seen them and take a picture of them thanks to the great results from the Event Horizon telescope. Some of these black holes are active, some others are less active, but we all agree that they are there. And black holes are also observed to very high redshift in booming quasars. And this is like a compilation of I hope, the most recent compilation of the redshift distribution of quasar high Z. We have more than 300 redshift greater than 5.5 of quasars, and this is like thank you to both spectroscopic and photometric surveys that were able to select and observe them. And as you can see, we get to very high redshift, and indeed the record is a redshift 7.54, and this was quasar selected using pan-star, so color selection, then spectroscopically confirmed from Bañados et al. It's a paper from last year, and this source is also X-ray detected with Chandra, and so it is a record also for the X-rays. The interesting part of these black holes, besides being the highest redshift, I mean, it's not that high because we know galaxies are even higher redshift, but the interesting part of this is that the black hole, the mass of the black hole hosted in this quasar is very high. It's like almost 10 to the 9 solar masses, and this is being measured with the broad emission line in the spectrum of this source. But this is not the only quasar showing a black hole with such a high, large mass. In fact, it seems that a lot of the quasars that have been discovered at very high redshift have masses that are above or around 10 to the 9 and even 10 to the 10 solar masses. In fact, the record, it's more than 10 to the 10 solar masses, still a redshift greater than 6. And this is like this is a huge big beast. And this is actually a problem. It's a challenge to have these big black holes at such a high redshift. It's a problem to form them. In fact, like to assemble such an high mass in such a short time, this would require uninterrupted Eddington accretion. I mean, accretion at Eddington since like a very, very high redshift. And this is very interesting because it puts strong constraint on the type of seeds from which this black hole could have formed. In fact, depending on the initial black hole, like if you have a black hole with the mass between 10 to the 4, 10 to the 6, so heavy seed, then to form these sources, you could have had like periods with lower accretion, not just at Eddington. But if you were starting from black hole like live seed with masses like 10 to the 3 or below, then it would require like even super Eddington accretion for such a very long time. And this is a problem because it's a challenge for black hole formation model, but of course this is just the tip of the iceberg. Of course these are the brightest sources that we are observing, and this is like totally an observational issue. There must be some sources with smaller mass, but we haven't detected them yet. The other place where we can get constraint on the black hole formation, not just the high Z, is also a low Z. In fact, we are now starting to detect massive-ish enough black holes in small galaxies at low redshift. And this is an example that was recently published by Baldassari et al. And this is RGG 118, is a dwarf galaxy. And a confirmed black hole with a mass of 5 × 10⁴ solar masses was reported for this source. And there are several other examples, and Igor, a few weeks ago, was telling us about black holes with the small mass black holes in local dwarf galaxies. And these local black holes seems to extend scaling relation. These like huge massive galaxies with the big black hole in the local universe seem to extend this scaling relation to low masses. And so the black hole formation models need at the same time to explain both the existence of these very high redshift massive quasar and also the low mass black holes in low mass galaxies in the local universe. You know all about black hole formation models, but briefly, there are two main options nowadays that we believe into and that are mostly considered. So one is like a black hole formed by direct collapse of gas clouds, and this will form like heavier seeds with masses of 10⁴, 10⁶ solar masses, this side here. And then there are like light seeds with masses of the order of 100 solar masses, and these would be formed from the remnants of the first generation of massive stars, so POP3 stars, what is called POP3 stars. Of course, probably you need a little bit of both to get to what we see nowadays, but this needs to be tested. So the way we are trying to test which black hole formation model is like the most accredited, or which one is the combination between the two, there are three possible ways, I would say. The first one is to look for the model prediction of observable. In fact, the two different models, direct collapse and POP3, will give us different results, as for example, on the black hole occupation fraction and on the scaling relation. So if we had like, direct collapse black hole will give us less black hole but more massive, while POP3 seed will give us more black hole but less massive. Instead, on the scaling relation, of course, if we had just direct collapse black hole, the scaling relation would flatten at masses of the order 10⁵, 10⁶ solar mass. Instead, if you allow for lighter seed, you could have a drop in the scaling relation at lower masses. And if we would observe a mix of the two, it would be interesting to understand the fraction again. The other option to understand the black hole seed would be to actually detect some of these small black holes in the very high redshift universe. And the searches are not very successful, I would say, but people keep trying. And one example is the galaxy CR7. This is the brightest Lyman alpha emitters in the sky, a redshift 6.6. And the first observation of this source, and this was in particular spectroscopy, emission and absorption line in the spectra of this source, suggested that this could host a POP3-like black hole. However, there were lots of papers that have been published about this object, and it was also presented last year by David Sobral. They gave this lunch talk in September. The reanalysis of the data of the source, the broadband data, suggested that actually this object could host a direct collapse black hole. And this mainly came from the modeling that was done by Fabio Pacucci et al. And Fabio was here, I guess, at the beginning of the year, showing the same exact source. And his modeling suggests that this could be a Compton-Tick, so very obscure direct collapse black hole with a smallish mass. And he has some option for the obscuration and metallicity level of this source. But this is still like not confirmed, or this is what we would like to believe about this source, but it's not confirmed, so we cannot claim a detection of a black hole seed in a redshift 6.6. So I've been looking into the Chandra data of this object, and there are currently 6 observations for a total of 180 kiloseconds, and there is no detection of the object in the broad band, soft or hard or full or anything. But when we were slicing the very soft band in narrow band, then we find 3 counts in the very soft 0.75 to 1.25 band. And this is like, in this way, you enhance the source counts and like decrease the background at the maximum. And of course, 3 counts is not a detection. Otherwise, we would have published it and being very famous about detecting the X-ray this source. But we try to model a little bit these 3 counts, and there are 2 options that we came around, and we think that either could be a high column density obscured source, and the obscuration is obscuring all the emission, that is at energies below 5.7 keV, or this is just a faint source that we don't detect, and we see only 3 photons because of a combination of like a power law plus the Chandra effective area, and this actually I think is what works the best. But with the upper limit on the luminosity that we get using these 3 counts, Fabio Pacucci rerun his models, and what we get with this luminosity is a more massive black hole. So we try to propose for more Chandra time, and I don't know, we'll see. But this would be exciting to try to understand whether CR7 is just normal AGN or is something more interesting. So anyway, detecting this seed black hole at very high energy is very hard, and we have not been successful so far. So what we've been doing with MAR, we are trying to detect what we call a population of leftover intermediate mass black holes. So if we look at if we think about the first black hole, either POP3 or direct collapse black holes, most of them, they should have like grown via accretion or mergers through the cosmic time until the very massive black holes that we see nowadays. But there must be a population of black holes that didn't accrete and didn't merge, and so that we could observe a low Z in some galaxies. And these black holes would have like masses very similar to what we think are the original black holes, so masses of the order 10 to the 3 to 10 to the 5 solar masses, 10 to the 6. So the place where to find these kind of leftover intermediate mass black hole is like dwarf galaxies. Dwarf galaxies are a good place to find these small black holes because, first of all, if we believe in scaling relation, small galaxies should host small black holes. And the other thing is that dwarf galaxies are dominated by supernova feedback. So supernova feedback basically deplete the reservoir gas at the center of the galaxy, so there is no accretion into the black hole. So if this dwarf galaxy really hosts this relic black hole, there shouldn't have, no accretion would have happened. So these are the real original relics from the early epochs. So this is interesting, and this is just an example of like some local dwarf galaxy, LMC, SMC, and so on. And there are some dynamical measurements of black holes in dwarf galaxies, and this is just a table from a recent review by Amy Rines and Andrea Comastri on the subject. And you see only less than 10 sources, less than 10 dwarf galaxies have a black hole mass that is measured through dynamical measurement. But you cannot do this for high-energy galaxies. Of course, it's not possible to have a dynamical measurement of the black hole mass. So the way to look for black holes in dwarf galaxies is to look for them when they are shining in the form of AGN. So searches of AGN in dwarf galaxies are challenging as well because these AGN are powered by small black holes, and this black hole, of course, has like of the order, like, say, 10 to the 5 solar masses, and even if they are accreting at Eddington, the luminosity would be 10 to the 43 erg per second, and this is not so bright, so you need to have deep observations, and you need to be really careful, because the luminosity of 10 to the 43 or lower is very comparable to the star formation luminosity, so you need to be careful what you're doing, and really properly recognize that you are actually looking at a black hole at the center of the dwarf galaxies. So multi-wavelength searches of AGN in dwarf galaxies have been going on, and there are different methods to select them. And Igor gave a presentation a few weeks ago about his work on the subject using optical emission line diagnostic. And there are several sources that have been discovered with X-ray and radio emission, but these are mainly single sources that have been followed up to confirm just that object. So we don't have big sample. The biggest sample is with optical emission line diagnostic, and Amy Rines have been working on it a lot, but they confirm only, let's say, like few tenths of AGN in dwarf galaxies, and all of them have masses of 10 to the 5 to 10 to the 6 solar masses, so quite massive black holes, so they don't get anything to 10 to the 4 or 10 to the 3 solar masses. And this might be an observational bias because they are mainly using SDSS and not very deep data, so this is what you can get. So with MAR, what we wanted to do is to extend these works to high redshift, and I forgot to say that these samples are all limited to redshift 0.6. So we wanted to extend to high redshift and have a complete sample so that we could derive the black hole, the active black hole occupation fraction, and then go back and compare with prediction from models. So guess what? We used the best survey available on the market. And this is the Cosmos survey, and I've been part of it for many, many years. And it's a great place. It's a great survey. We have a lot of data, and we detected like 2 million of galaxies in the 2 square degree field. And at this point, we have a lot of data. I think 43 photometric bands, and from both ground and space-based observatory, name it, and we have it. And mainly, I've been focusing on the X-ray, as you know, using both Chandra and NuSTAR. But for this work, we decided to use both X-ray but also radio for our to detect AGN in dwarf galaxies. So we selected 4 from our galaxy catalog. We selected the low mass galaxies with masses less than 3×10⁹ solar mass. This is just a value that was decided. I think it's the mass of the LMC. It was decided as a limit of between dwarf galaxies and massive galaxies. But anyway, that's it. So we have more than 52,000 dwarf galaxies in the field, and this is just the mass distribution. And less than 1% of them are detected in the X-ray, and up to redshift 2.4, and less than 1% of them are detected in the radio band to redshift 3.4, and the 2 samples they don't have any source in common, so it's very interesting. We can do different studies with both of them, and the results of this work have been published in 3 different papers, one of which was just submitted last week. So first of all, we started to look at the entire 52,000 galaxy sample, and we performed X-ray stacking analysis, and we selected and divided the sample in complete beams in redshift and mass, and this is the redshift versus luminosity or mass distribution, and those colored boxes are the 5 beams that we divided the sources into, and we performed stacking in the X-ray with Chandra data. And these are the 5 stacked results. And as you see, we get significant X-ray emission in each beam, and we get the detection up to redshift 1.5. Of course, these are luminous, not so luminous sources. They are faint, and you need to be careful how much of these X-ray luminosity come from X-ray binaries or hot gas. So we just use standard scaling relation to subtract the contribution of the X-ray binaries and the hot gas, and we are still left with some nuclear luminosity. And in here I'm showing the nuclear luminosity, so AGN luminosity versus stellar mass for both the stacked 5 beams and also the 40 detections, individual detections. And so first of all, what we can notice is that we can detect AGN in dwarf galaxies to redshift 2.4. This is the highest redshift source that we have. We have luminosity to redshift 10⁴, so clearly we have AGN in these sources, and this is just nuclear luminosity. And we are covering like 5 decks in luminosity, so we have any kind of like super powerful and fainter AGN in this sample. If we look at the individual detections, and then we use local scaling relation for dwarf galaxies that Amy Rines and Marta Volonteri published a few years ago to convert the stellar mass to black hole mass, then we can have an estimate of the black hole mass for these 40 detections. And then using bolometric luminosity, we can also derive the accretion rate of these sources. So we see that we cover like 2 decks in black hole mass. We have lots of sources at the higher end, but we have several objects with masses like less than 10⁴, and this would be the lowest mass black holes in dwarf galaxies if these were actual real measurement. And also we find them to be really accreting, and the accretion is like 10 to the minus 1 Eddington, and some of them are very close to Eddington, as you can see here from the color scale. And of course, we don't have real black hole masses, because just assume using scaling relation, and this is why we ask for 30 hours at GTC to follow up 8 of these intermediate mass black hole, and 2 of them are in the lowest mass bin, so we can measure the black hole mass from the broad emission lines. And we are really looking forward to this data that are coming. So what we did with this sample, we measured the black hole active occupation fraction, and this is mainly with the both detection and none. And we can measure the occupation fraction using in 2 different luminosity bins, faint luminosity and bright luminosity. So for the faint luminosity bin, we can measure the occupation fraction in 2 mass bins. And what we find is that the occupation fraction decreases with mass. So it decreases with decreasing mass. And when we compare with the model prediction, this is in agreement with simulation for dwarf galaxies with direct collapse black holes. So direct collapse black hole predict a decrease in occupation fraction with decreasing mass. And of course, this is not the true occupation fraction, it's the active occupation fraction, which is a lower limit, but this is already like a good indication. And in the bright luminosity bin, a high luminosity, we cannot compute the occupation fraction in different mass bin, only in the high mass bin, but we can measure like evolution of the occupation fraction in 3 different redshift bin, and this is like really new. There was only another work before that was done measuring the evolution of the occupation fraction, and we see like that the occupation fraction is decreasing with redshift, and this is completely different from what is observed for high mass galaxies, and this is just a figure of the AGN fraction as function of redshift by James Hurd et al. And here is showing that the AGN fraction increase with redshift for massive galaxies. These are all massive galaxies. He had also found an hint of decrease for the dwarf galaxies, and these are the 2 points that we are plotting there, but he totally overlooked it. And so we just pointed out this to him, and it seems that dwarf galaxies evolve differently than those in high mass galaxies. And this is very interesting, and it seems that the black hole growth seems to be suppressed in the low mass regime. So the other thing that we did, we used the radio survey in the cosmos field. This is a project that has been led by Vanessa Smolcic. She has this 2 square degree survey, 384 hours, 3 gigahertz. This is like, I don't know, and I'm not a radio expert, but it seems to be the deepest and the highest resolution survey that you can do, and that is on the market. And it's indeed very cool data, and they can probe very faint radio sources to redshift 4. And they detected more than 10,000 sources, and they did a great job. She had an army of postdoc and students to look at this data, and they did a very good data quality assessment. And so we got their catalog, and we selected dwarf galaxies with radio emission, and we have 43 of them, and these are the radio images. And for 41 sources, the radioluminosity was higher than what we were expecting from star formation. So in the end, we went only with the sample of 41, and we excluded 2 that were the radioluminosity was just dominated by star formation. And 35 of them have compact radio emission, so definitely radio emission coming from the nucleus, and the sample extend to redshift 3.4. In general, it seems that both the radio and the X-ray dwarf, radio and X-ray detected dwarf, seems to have lower masses than what has been reported, like, for example, by Amy for optical AGN in dwarf galaxies. And also we can extend to very high redshift, like with the X-ray sources we were going to redshift 2.4, and with radio we can extend to 3.4. So what we've done with these radio AGN in dwarf galaxies, first of all, we have computed all sorts of luminosity, radio luminosity, volumetric luminosity, and what we observe is that once we subtract the contribution from star formation to the radio luminosity, we find fairly luminous sources with nuclear luminosity between 10 to the 37, 10 to the 40, and we also compute the kinetic power using Merlonian-Hines recipe, and we get fairly high kinetic power, 10 to the 41 to 10 to the 44 Hz per second. And this seems to be not something that we were expecting for dwarf galaxies, more like consistent with what you would expect for massive galaxies. And also the jet efficiency, that is like some kind of conversion from kinetic power and bolometric luminosity, is very high. Again, similar to what you would expect for massive galaxies. And so we were really surprised because we were thinking, oh, we are going to see something very similar to our X-ray results. Instead, like these dwarf radio AGN in dwarf galaxies seems to be booming very bright sources, and we seem to observe like AGN feedback in action instead of supernova feedback in action. That is now what we were expecting, and this is like totally against the fact that these intermediate mass black holes are like a very quiet, not growing black hole in dwarf galaxies, but they seem instead to maybe start to grow nowadays. We don't know exactly what the time scale has been this object been growing for a long time or not, but this is not consistent with the picture where dwarf galaxies were hosting the relics of the early universe. So if we go back to this picture where we have the first black holes in the universe and those that accrete and merge this way to form the big quasar, then these leftover intermediate mass black holes in dwarf galaxies, they don't seem to be that leftover anymore, or at least not all of them, not the radio one, not the one that we observe in the radio band, because we definitely see some AGN feedback, and also there have been several works showing that some of these dwarf galaxies where we detect black holes seem to be in merger, and this is an example of a dwarf-dwarf galaxy merger pair in Markarian 709. So definitely not the quiet, doing nothing kind of galaxies that we were expecting to be. So definitely these, at least in the radio sample, are not the relics of the primordial black holes. So this would be my summary. We are trying to understand black hole seed, and we are going around the fact that we don't detect them at higher redshift by looking at more local sample of intermediate mass black hole, both in X-ray and radio. And what we find from X-ray and radio is kind of different, and definitely the intermediate mass black hole in dwarf galaxies that are detected in the radio might not be the untouched seeds. And just because the answer to everything is links, then I just wanted to leave you with the conclusion that the future is bright, and once we will have like links, we will be able to truly detect these seeds black hole at very high redshift 9, 10, 11, and there will be tens, if not hundreds of them, and this depends from the different formation model that you want to believe. But I mean, bright times are coming, and so we will have definitive answer then. Thank you. Oh, and I forgot, credit to Grant. I don't know if he's still here for the figure.
Have you looked at the masses of this IMBH from the radio X-ray luminosity?
Yes, we did, but unfortunately, none of these radio detected are X-ray detected. So, yes, there are no sources in common. The X-ray detected don't have any radio, and the radio don't have any X-ray. But what we did, we just did some stacking of the radio detected in the X-ray, and what you get is just a limit on the luminosity, so it's not super useful. You just give even broader constraint on the black hole mass. And it's like everything in between 10 to the 5 and 10 to the 8. So.
First, to comment on this, the X-ray radio correlation has a dispersion of 1 dex. So it's virtually useless in
Yeah.
this regime because you cannot distinguish between IMBH and normal black hole.
Yes, it's
But I wanted to ask you about something different. I showed in my presentation 3 cases under 3 times 10 to the 5 at the accreting at the Eddington limit, and one is at 70,000 solar masses of black holes. So it's like a real IMBH.
Yeah, yeah.
And this is the thing that
sorry
is
if I didn't-
very, very, very bright, and you should be able to see such stuff at redshift of 0.5 if, like, those galaxies are, if those black holes were, well, if we assume that there was no substantial evolution.
so I think this thing here that these X-ray detected ones that are the one that I know better because it's more my field and so I know what I'm looking at. These are definitely super bright sources, and the masses are, the Oz galaxy masses are, we are very confident in the masses. So
How does it go in line with your claim that normally the IMBH should be in quiet dwarf galaxies and not growing?
But so this is the thing. I think this is interesting to look at the active fraction here. The fact that the active fraction decreased with redshift is telling us something like they are just starting now to be active. These sources here are not as active. Most of them are actually not that growing, and so this is like.
Can this like a selection effect? Because if they're not accreting a lot of material, we won't see them, especially at higher redshifts.
Yes, and I guess this is like the way why we went to try to do the stacking, and definitely we find sources that are not as luminous, and these are definitely not accreting at Eddington. This is like low luminosity sources, and there is definitely a spectrum of, some of them are definitely not active, and then you see some instead that are brighter, and they are just starting now to become more active.
Yeah, I have a related question. So when you look at your occupation fractions, how much you may have some systematic bias, also how you're subtracting the formation rate from the Wilks galaxy and the redshift dependence on that as well. So how confident can you be that there are these trends with redshift and mass?
So this is this was one of the questions of the referee. Are you sure this is complete? The correct for all the factors, blah blah blah, and so.
Because there is also the redshift evolution.
There is the redshift evolution. So we are trying to take into account for all of these things. But as you can see, our sample goes to 2.4, but here we just stop at 0.7 because there is nothing that we can say above that, and definitely you enter in the incompleteness and issue of all the kind of correction that you can apply. And also we're being really careful, like in the low luminosity range, we have only one redshift beam that is just basically all the sources are low Z. So I think that we are quite confident on this. It would have been nice to extend to higher redshift, but I was just hand waving. And we are confident on all the correction applied here. But keep in mind that this is just the active occupation fraction, not the total one, and so definitely a lower limit on it. It can be, it can totally change the shape depending on the one that you don't see.
Also, one must say that the error bars are pretty big.
Error bars are big, although everything that has been reported about this in the literature is in this figure. So there is only this kind of upper limit with this error here and another upper limit there, and so having some, we are moving, so, we are making steps just beyond the local sample. And
All right. Francesca's obviously around, so you can continue this discussion later. All right, let's thank both our speakers.
thank you.
I'll just send you this plot that I made. It might be of use. Yeah. I made it a few years ago, but I basically did simulations to figure out how low a mass you could get to with links. And this is for old responses. It might have changed a little since then. But you will actually get a small handful of 10 to the 4th out to a redshift of about 7. Looks like beyond that, you're going to be hard pressed, but you could get a few 10 to the 5th.
Yeah.
Anyway.
Although this is like so.
That's assuming they're accreting at Eddington.
Did you see this recent paper by Zoltan, Hyman, and Alexei was submitted as a white paper to the Decadal?
I haven't read it, but I saw that it was.
So they have prediction of detecting with masses of 10 to the 4, 10 to the 5. They have prediction of detecting them at Redshift 11 in tens to hundreds of them.
Really? Because this was a megasecond observation with the HDXI responses, Eddington limit, and that was making a fairly conservative assumption about,
I've heard many things about it, and there was a lot of arguing back and forth about those predictions, and they had originally we will detect 1,000, and so then there was a lot of arguing back and forth by several co-authors of that paper. You should I'm going to send that to you.
Yeah, I'd be
They
interested
put
to see
it
that.
on archive, I guess.
I'll forward this figure to you too, just so you have it if you want a point of comparison. Like I said, I can always update it with new responses, but this is just the number of counts. So again, you're not going to see any counts out to Z of 10 for 10 to the 4th.
Yes, I'm curious to have your opinion about what they put out. And that was, I think that was with 4 megaseconds.
Okay.
But really, they are saying that in a survey, so the idea is to do 1 square degree survey. So I'm going to show you again this figure. Sure. So this is their prediction for the links deep. So they would be 4 megasecond, I guess, on a 1 square degree field, say half the cosmos, 4 megasecond links.